Hey everyone, I wanted to shoot a video to show you how electromagnetic induction works. So I'm sitting at my work table. I've got some old sandpaper here. I've got some copper wire. It looks red because it's got some enamel coating on the outside of it for protection. I've got a package of LED lights. This is what one looks like up close. These are some neodymium magnets. Sometimes they're called rare earth magnets. And then this is a galvanometer. You remember from the last unit that electric charge is measured in coulombs. When you have a certain number of coulombs passing a point per second, that's called amperage, because a coulomb per second is an ampere, or amp for short. Current is a type of speed. It's a rate, okay? So this galvanometer, there's a needle here in the middle. The A here that you see stands for amp. The little letter in front of it that looks kind of like a U with a little tail on it is the Greek letter mu, or mu. I've heard it pronounced both ways. We use it to stand for the Greek prefix micro. If you put micro in front of a metric unit, it means 1/1,000,000th of that unit. So this galvanometer measures electric current in microamperes. Everything to the left of 0 is on the negative side. Everything to the right is on the positive side. Okay, so what we're going to do, we're going to move everything over here. We're going to hook up some electric wire to the galvanometer, and we're going to see what happens. So what I did, I took some copper wire and I coiled it about 400 times around this syringe. You can use any tube that you want. You don't even have to have a tube. It just makes it easier. This is just a syringe that I use to give my dog medicine. So there are two ends of the wire, or the coil. So what I'm going to do is wind each end to the galvanometer. To wind it a couple of times and then screw it down so you have good contact. And I'll do this on the other end as well, to the negative end of the galvanometer. Okay. And everything that I got here, I found at Amazon. You could find some of this stuff at Radio Shack. The galvanometer you could find at Home Depot, but it wouldn't look like this. It would be a digital one. I wanted this one because I wanted you to be able to see the needle move back and forth. Okay, so I'm going to stick the magnets inside here. And you'll notice that if it's just sitting in the coil and not moving, the needle's not moving either, is it? But look what happens if I move the magnets. The needle starts to move, doesn't it? Okay, and it moves from negative on both the negative end and the positive end. Remember that this coil of wire has about 400 turns of wire on it, and so it goes from about negative 400 to about 400. Okay, all right, so let's pull that out. I'm going to disconnect this one. And we're going to get another coil of wire. Okay, I've got another syringe here. You can tell that this coil is smaller. This one only has about 100 turns of wire. Okay, I'm going to hook this up to the galvanometer just like I did the other one. And we're going to do the same thing. I'm going to pass the magnets through, and I want you to watch the needle this time. What do you notice? The needle isn't going as far to the left or right of 0 as it was earlier, is it? Okay. In fact, it goes from about negative 100 to about 100. Okay. So what's the relationship between the number of coils of wire you have and the strength of your electric current? Okay, based on what you've witnessed, you can tell that the more coils you have, the stronger the electric current. And again, if the magnets are just sitting there, there's no electric current passing through, is there? The magnetic field has to change for electric current to pass through. Okay, so this is all fine and good. Let's use a practical application for this. So I'm going to disconnect this coil. And I'm going to get the coil with 400 turns of wire around it again. But instead of hooking it up to the galvanometer, I'm going to hook it up to the LED light. It's got two electrodes here. and you want to make sure that you get really good contact. So you want to make sure that you turn the wire around each electrode several times to ensure good contact. And it's a little bit tedious. It kind of takes some doing. Okay, so now I've hooked this up to the LED, both ends of the coil, and I want you to watch what happens. If I just pass the magnets through slowly, nothing's happening to the LED, is it? Okay, but watch what happens if I move it quickly. You see it lighting up? Okay, so that's electromagnetic induction. Okay, the word induction comes from the word induce. So if you induce something, that means you're causing it to happen. Okay, so if you're inducing electric current, you're causing it to happen. And the only way that that happens is if the magnetic field, which is caused by the magnets, is moving constantly. Okay, if you have any questions about electromagnetic induction, please feel free to reach out to your teacher. One more thing that I wanted to point out about this galvanometer, whenever we were passing the magnets through the coil, remember the needle was going back and forth, wasn't it? Okay, there are two types of electric current. You have direct current and alternating current. Alternating current simply means that the current is changing directions, and that's what the needle is indicating here. So as the magnetic field changes directions inside the tube, the needle goes back and forth, okay? Thomas Edison, when he discovered the light, or when he invented the light bulb rather, that was an example of direct current, okay? Then later on he had a young man working for him named Nikola Tesla. He was the one who came up with alternating current. Most of your appliances today run on alternating current. It is more efficient than direct current. So I wanted to show that to you. So this is an example of alternating current, and you can tell because the needle is alternating or going in both directions.